So here's how it works. We have to explain a paradox. Here's the paradox. Who has children? Enough of you. What happens if you give a 5-year-old kid a cookie? Yeah, they eat it. Yeah, I know they eat it. Yeah. What happens after that? They bounce off walls is what they do. Ask any kindergarten teacher what happens when the cupcakes roll out for the birthday party. Okay? That's the end of the lesson. Okay? They're bouncing off walls. It's known as the sugar high. So what's going on? The fat cell gets filled with, because of the cookie. The leptin goes up, tells the brain, hey, I've got extra energy on board. It tells the sympathetic nervous system, the fight or flight part of the nervous system that innervates your muscles and innervates your fat cells, hey, I got too much energy. So what happens? You burn it off. So the sympathetic nervous system tone to the muscles give you the fidgeting, and the sympathetic nervous system tone to the fat cells releases the extra fat, and that gets used for energy later. And so this is a nice negative feedback pathway that keeps you in energy balance as long as your brain can see its leptin. So far, so good. So here's the paradox. What happens if you give an obese 5-year-old kid a cookie instead? They're in the pantry looking for more cookies. Anybody ever see a sugar high in an obese kid? Doesn't exist. Doesn't exist. And that's why they're obese, is because they don't get the sugar high, because they can't see their leptin. Because if they could see their leptin, they'd have a sugar high. But they don't. That's the point. So something's blocking that leptin signal. That's the paradox. And the question, what is it? So we learned about leptin from this patient over here. Okay? This is the OB mouse, the leptin deficient mouse, who has a gene defect in the leptin gene. So this animal's leptin is 0. So his brain thinks he's starving all the time. So he'll eat anything in sight. Not only will he eat anything in sight, but this animal is the ultimate couch potato, because his brain can't see his leptin, so he thinks he's starving, so he doesn't want to burn energy, he wants to store it. So the only reason this animal ever gets off his hiney is if you put the food on the other side of the cage, then they'll waddle over to that, sit down, eat it there, and stay there instead. Okay, everybody got it? Now, the reason? Because leptin tells the hypothalamus that you've got the energy to burn. So if the hypothalamus sees the leptin signal, then this diamond over here gets activated. Anorexigenesis, that is, I'm not hungry, I don't need any more, and I can burn energy effectively. And so it tells the sympathetic nervous system turn on to fidget and to release fat from the fat cell. And it tells the vagus nerve, the energy storage nerve, hey, I'm not hungry, appetite down, and stop releasing insulin. Everybody with me? Conversely, if the leptin doesn't reach the hypothalamus because there's a gene deletion or because there's something blocking it, then you get this diamond instead, which is orexigenesis. I'm hungry. I need more food because I'm starving, and because I'm starving, I'm going to try to conserve. And so that means your sympathetic nervous system tone goes down, which means you sit on a log, and your vagus nerve goes up to increase your appetite so that you'll generate more calories in order to put more into the fat cells to try to get more of a leptin signal. Everybody with me? And this is that same negative feedback pathway I showed you before. It's now schematized. Okay. And there are leptin deficient people, 14 at last count. 14. And they're all of consanguineous marriages, and they're all of Pakistani or Turkish ancestry. And when they're born, they're perfectly normal weight. And by age 6 months, they're already massively obese because their brain is constantly starving. It doesn't matter how much weight they gain, their brain can't see it because it ain't there, because they have a leptin gene defect. So here's a patient, 220 pounds by age 9. Okay? But you start giving them shots of leptin every day, and look what happens. They lose weight on a dime. And it's all fat mass that they're losing, too. Hormone replacement therapy, because now their brain can see leptin because we're giving it to them from a bottle instead of from their own fat cell. Hormone replacement therapy, that's what I do as an endocrinologist. That's my job. And here's an example. Here's the patient at 3.5 years of age, looking pretty awful. And here's after a shot of leptin every day for 4 years, indistinguishable from normal, because we fixed the problem. Great, right? For those 14 people. The problem is the rest of us are not leptin deficient. The rest of us are leptin resistant. We got boatloads of leptin, and the leptin correlates with how much body fat we have. But if our brain could see that leptin, we wouldn't be obese, because we'd burn it off in the sugar high, right? Everybody got it? So there's something blocking that signaling right there, that X. That's the holy grail of obesity, right there. What is blocking leptin from working? Because if your hypothalamus can't see it, then you're in this box over here, and you can see things just go in the wrong direction, and there's your gluttony, and there's your sloth.